Example 2, page number 90. Example 1 is an easy question. You can try by yourself. Let's now do example 2. Prove that 2 raised to n greater than n for all positive integers. So P of n statement is 2 power n is greater than n for all positive integers. Now P of 1 is 2 raised to 1 greater than 1, and it is true. So P of 1 is true. P of k statement is 2 power k is greater than k for all positive integers k.
That is, we are assuming P of k to be true here.
Now P of k plus 1 statement, which we have to prove, is 2 power k plus 1 is greater than k plus 1. 2 power k plus 1 can be written as 2 power k into 2 power 1. Now I am going to replace 2 power k using P of k statement, this one. So since we have greater than sign, I have to replace it by greater than k times 2. Now this 2k can be written as k plus k. Now let us replace this k by 1, because we know that k is greater than 1. Already for k is equal to 1 we have proved the result. So we are trying to prove the result for the other values of k, which are more than 1. So k is greater than 1. 4 is greater than 3. So you may replace this 3 by a still smaller quantity. The inequality holds good. Okay, that's what we are doing. So we are replacing k by a smaller number, 1. Therefore, we have proved that 2 power k plus 1 is greater than k plus 1. And it is true for all positive integers. Therefore, P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Example 3 is an easy question. Try by yourself. Now let us do example 4. For every positive integer n, prove that 7 power n minus 3 power n is divisible by 4. P of 1 will be 7 raised to 1 minus 3 raised to 1. 7 minus 3 is 4, and it is divisible by 4. Therefore, P of 1 is true. Let P of k be true, and the statement is 7 power k minus 3 power k is divisible by 4. Since it is divisible by 4, it should be a multiple of 4. So we will write it as 4m. P of k plus 1 statement is, that is the statement to be proved, 7 power k plus 1 minus 3 power k plus 1 is divisible by 4. Let us take this expression and split the power as 7 power k into 7 power 1 minus 3 power k into 3 power 1. Now from this p of k result, 7 power k is 4m plus 3 power k. Let us use this result to prove p of k plus 1. Which is 4m plus 3 power k times 7 minus 3 power k times 3. Open the brackets, 28m plus 7 times 3 power k minus 3 times 3 power k. These two are like terms. Simplify. 7 minus 3 is 4. 4 times 3 power k. Now 4 is a common factor. And this is divisible by 4. Therefore, p of k plus 1 is true. Whenever p of k is true. Therefore, p of n is true for all n belonging to capital N. Example 5. Prove that 1 plus x whole power n greater than or equal to 1 plus nx for all natural numbers n. And here the condition given is x is greater than minus 1. Let us first show that p of 1 is true. Substitute n as 1. So 1 plus x greater than or equal to 1 plus x. We have equal to sign. Therefore, we can say that p of 1 is true. Let p of k be true. And p of k statement is 1 plus x power k is greater than or equal to 1 plus kx. And it is true for x greater than minus 1. Now the statement to be proved, p of k plus 1 is 1 plus x whole power k plus 1 greater than or equal to 1 plus k plus 1 times x. Let us take this 1 plus x whole power k plus 1, the left hand side. I can split the power as 1 plus x whole power k into 1 plus x. Now I am replacing this 1 plus x whole power k. I am using this p of k statement. So it becomes greater than or equal to 1 plus kx into 1 plus x. Let us multiply 1 plus x plus kx square. Therefore, 1 plus x whole power k plus 1 is greater than or equal to 1 plus, I can take x common from the second and the third terms, and I am leaving this kx square term. We know that kx square is positive. K is a positive number because it is a natural number, and x square is positive because of square. So kx square is greater than or equal to 0. For example, if 4 is greater than 2 plus 1, 1 is a positive number. If I leave that positive number and write, the inequality holds good. So similarly, we are leaving that kx square and writing the remaining terms. So the inequality holds good. Therefore, P of k plus 1 is true. Whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Example 6. Prove that 2 into 7 power n plus 3 into 5 power n minus 5 is divisible by 24. So P of 1 statement is 2 into 7 power 1 plus 3 into 5 power 1 minus 5. Let us simplify this. 14 plus 15 minus 5, which is 24, and it is divisible by 24. Therefore, P of 1 is true. Now, let P of k be true and write P of k statement, which is 2 into 7 power k plus 3 into 5 power k minus 5 is divisible by 24. If it is divisible by 24, it will be a multiple of 24. So I can take it as 24m. Now from this, 2 times 7 power k is 24m minus 3 times 5 power k and plus 5. To prove P of k plus 1, which is 2 times 7 power k plus 1 plus 3 times 5 power k plus 1 minus 5 is divisible by 24. Two times 7 power k plus 1 plus 3 times 5 power k plus 1 minus 5 is equal to, I can split the power and write it as 7 power k into 7. Similarly, 3 into 5 power k into 5 and minus 5. Let us substitute for 2 times 7 power k from P of k statement. It is 24m minus 3 into 5 power k plus 5 into 7 plus 3 5s are 15. I can multiply and write. So 15 times 5 power k minus 5. Let us multiply and write 24 into 7m. No need to multiply 24 and 7 because we have to take 24 out. And this is 7 3s are 21 times 5 power k plus 35 plus 15 times 5 power k and minus 5 equal to 24 times 7m. Here we have minus 21 5 power k and plus 15 times 5 power k. Minus 21 plus 15 is minus 6 times 5 power k plus 30. 24 into 7m. Here minus 6 is common. We get 5 power k. Since we have taken minus 6 out, we have to write minus 5 here. But we need 24 as a common factor. We have only 6 here. So we need to prove that this is a multiple of 4. So 6 4s are 24 it will become. Now we are going to prove that 5 power k minus 5 is a multiple of 4 we are going to show. So let us take k is equal to 2. K is equal to 1 already we proved. The result is true for k is equal to 1. P of 1 we proved already. So let us take k is equal to 2. If k is 2, 5 square minus 5. 5 square minus 5 is 20. If k is equal to 3, 5 cube is 125. 125 minus 5. Which is 120. And then if k is 4, 5 power 4 is 625. 625 minus 5 is 620. If you see, all these numbers are multiples of 4. Therefore, I can conclude that 5 power k minus 5 is a multiple of 4. Since it is a multiple of 4, I can write this as 4p. Don't use 4m because already we used m. So it becomes 24 into 7m minus 6 times. I can write 5 power k minus 5 as 4p because it is a multiple of 4. Now 24 is a common factor which can be taken out. So 24 times 7m minus p, and it is divisible by 24. Therefore, p of k plus 1 is true. Whenever p of k is true. Therefore, the given statement p of n is true for all n belonging to capital N. Example 7. Again, this has an inequality. The given statement is 1 square plus 2 square plus etc. plus n square greater than n cube by 3, where n belongs to capital N. Now p of 1 will be, this is again a series, p of 1 will have only the first term greater than 1 cube by 3. Yeah, it is true. So p of 1 is true. Now let p of k be true. And p of k statement is 1 square plus 2 square plus 3 square etc. up to k square is greater than k cube by 3. To prove p of k plus 1 statement, which is 1 square plus 2 square plus etc. I am writing the kth term and then k plus 1th term. We have to show that it is greater than k plus 1 the whole cube by 3. Now for the first k terms, we know the total by P of k. So I will write the left hand side 1 square plus 2 square plus etc. k square plus k plus 1 the whole square. Now the total is, this total is greater than k cube by 3. So I cannot write equal to sign, I have to replace it by this inequality, k cube by 3 and plus the last term. Now let us take LCM and simplify. Therefore this expression will be k cube plus 3 times k square plus 2k plus 1. And this will be k cube plus 3k square plus 6k plus 3. Now 1 square plus 2 square etc. k square plus k plus 1 the whole square is greater than this. So towards the right hand side I have lesser sign. So I can change the terms, I can replace the terms by smaller quantities. The inequality doesn't change. So k cube plus 3k square, and I am replacing 6k by 3k and 3. I am replacing 3 by 1. I have replaced this 6k by a smaller quantity 3k and this 3 by a smaller number 1. So the inequality holds good. Therefore 1 square plus 2 square plus etc. k square plus k plus 1 the whole square is greater than 1 by 3 times. I can write this as k plus 1 the whole cube. That's what we have to prove. So P of k plus 1 is true whenever P of k is true. Therefore, P of n is true for all n belonging to capital N. Example 8. Prove the rule of exponents, that is ab whole power n is equal to a power n into b power n. P of 1 will be ab whole power 1 is equal to a power 1 b power 1 is true. Now let P of k be true. And P of k statement is a b whole power k is equal to a power k into b power k. Now to prove P of k plus 1 statement, which is a b power k plus 1 is equal to a power k plus 1 into b power k plus 1. The left hand side is ab whole power k plus 1. I can split this power as ab power k into ab. I can write this as a power k b power k using P of k statement. Now this is a power k times a into a and b power k into b. That is, we are using associative property. These are ordinary multiplication, so we can interchange and write, does not matter. This becomes a power k plus 1 and this becomes b power k plus 1. Therefore, p of k plus 1 is true whenever p of k is true. Therefore, p of n is true for all n belonging to capital N. Thanks for watching and please subscribe the channel.